So I'm very honored to be here today to open up this workshop. And one reason is, as people have said already, it's a very exciting time in terms of directly imaged exoplanets. So Don mentioned there's been 15 or so other workshops of this sort here. And some of these, 10 years ago, it was like, well, it's going to be very exciting when we directly image exoplanets. It should be any day now. And it is very exciting now that we do have, on order, 20 or so directly imaged planets. And amazingly, I'm the first person to show this slide because you're probably going to be seeing this slide a lot this week. And what's even more exciting is that we're likely to add more objects to this small but growing cohort in the next couple of years. So these systems, I'm not going to really talk about them very much because you're going to hear a lot more from Travis next, but they range from somewhat similar to what we see in our own solar system, like Beta Pic B. It's an 8 to 10 Jupiter mass planets at 8 to 10 AU from its star. So like a scaled up version of Jupiter or Saturn, which makes sense because this is a higher mass star. And then you get things like HR 8799, B, C, D, and E. So it's one A star with 4 planets. So they range from similar to quite puzzling. And the real advantage is that with light from these objects themselves, they are really valuable for characterization in terms of really, in particular, determining atmospheric properties from both photometry and spectroscopy. I'm not going to really talk about that, but just note that as we detect more, we're going to learn more and more about that. But the other thing that's really important about this small but growing cohort of objects is that we can start learning about demographics, about the architecture of planetary systems, especially wide planets, such as you find with direct imaging. And whether or not you find planets, you can start to talk about architecture because you can open up certain parameter spaces when you've sampled it highly enough. Oh wait, I have this thing. It's exciting. Anyway, so here is the parameter space we're talking about with both directly imaged planets and other techniques. So as you all know, transit planets tend to be very close in within inner AU. RV moves out a little further out. If you want to know what's going on past about 10 AU, direct imaging is really the only sort of technique that samples this. As we push down sensitivity, we notice that we really pretty much detect planets everywhere we have sensitivity to them. So the big goal in the future is basically to open up sensitivity to this area. So I'm going to talk about how we might do that, but also how we opened up the parameter space to find these objects as well, especially through large surveys. So I'm just going to kind of go step by step in terms of how we open up parameter space for direct imaging. Step 1, especially from the ground, that looks pretty weird actually. It's supposed to say on the top, to look at young stars. And the point here, it's splitting, yeah. All right, so I'll keep on talking about what that, you could see the slide. Yes, focus on young stars. And the idea here is that young stars host young planets, and young planets are pretty much brighter at younger ages than older ages. So here is just some very old evolutionary models, and you can see stars basically converge and hit this main sequence. Planets and brown dwarfs here just monotonically decrease in brightness with age. So if you can catch them early, you're going to get a more favorable contrast ratio between the star and the planet. So these are optimistic hot star models, which are when you take a big ball of gas and basically let it collapse into a planet as if a planet formed like a star. And that may not exactly be the case. Maybe a more realistic model would be more of a cold start model where you start by accreting onto a solid core. So here are comparisons of both hot and cold star models. And while you see hot star models give even brighter planets at early ages, the fact that planets start out a bit brighter and cool monotonically with age is true across both of this sets of models. So that's step 1. And then we have what I've called step 2, but is really more like step 2, step 3, step 4, step through infinity, is overcoming the technical difficulties in doing this. So I'm going to talk about the different parts that go into this and the different issues we need to overcome. The first one is the obvious one, is that there's a huge contrast difference between planets and stars. So for Jupiter, we're talking a factor of 10 to the 9th. As I mentioned already, we can sidestep this a bit by looking at young planets. And that gets us more to factors of 10 to the 4th, to 10 to the 7th. But then, to really get to these contrasts, the first step is you need to do something to get rid of the atmosphere. So you have the option of either going and working from space or using adaptive optics from the ground. I won't go into the details of adaptive optics, but what it basically does for you is take all this light that was in the seeing limited halo and just being scattered about by the atmosphere and stuff it back into the core of the point spread function. And once you've done that, if you have a candidate companion hiding in that halo, you might be able to image it. So that's step 1, and that's pretty much industry standard. Step 2, which we'll hear a lot about this week too, is coronography. This works better the higher Strel ratio you have, i.e. the better corrected your image is compared to the diffraction limit. And this is just one possible chronograph architecture. We're probably going to hear about a lot of others. But for the most part, chronographs consist of a simple part and a hard part. So here's the simple part here in this first focal plane. You take an occulting spot and you block out the star, right? So if you don't want to look straight in the sun, you can put your hand in front of it. That's basically all you're doing. And then the more complicated part is here in this second pupil plane where you have this Leo stop. And what it essentially does is correct for the diffraction pattern of the telescope. So combining these two, you can remove pretty much up to 99% of the incoming starlight and get much higher contrasts. And I'll note that, again, you need pretty high Strels for both of these to work. So some of the existing chronographs out there on ground-based telescopes, they work at maybe 60 to 70% Strels. So you're really using the occulting spot, and the Leo stop may not be doing all that much for you in that case. So those are the techniques you would use to get higher contrast, but still, even so, you have a second problem to contend with, which is speckle noise. So this is 2 minutes of AO data from NACO at the VLT, smoothed it and subtracted it from itself, and it's removed the smooth stellar halo. And what you can see left over is all of these little speckles, right? So these are basically little images of the star itself that have been scattered out of the coherent light train, basically by little imperfections in optics or leftover atmospheric residuals. And the problem is this pattern doesn't stay put. It evolves from the ground, minute to hour timescales. And you have this in space to do things like breathing and HST, and that involves on hour to day timescales. So you can't just integrate longer and get a higher signal to noise. You hit this limiting speckle noise floor. And so you need to use some sort of instrumental or algorithmic method to remove this speckle noise floor. Here's a technique that you're also probably going to hear a lot about this week. And this is the movie that may or may not work on us. So let's see. It works. Yay. All right, so you can look at either side because this is just from a dual imaging camera. I'll probably need to play this a couple of times. And what this has been done here is that the rotator is turned off during this telescope sequence. So you can see that the star and the speckles just kind of wobble about, and the real object in the field moves on the sky with a parallactic angle. Now, this thing pops right out as just a background star, but if it was closer in, this would be a way of decorrelating a real object from the speckles. So you can simply derotate and stack, and you've already done better than you would do if you had just not turned the rotator off. But what's more powerful, and again, we'll hear a lot about this, is to use powerful algorithms to combine all the different images in your stack of images and create an ideal PSF. So these are algorithms like Loki and different PCA variants of that as well. And so that is the next step. So these then are the 3 big elements of exoplanet imaging from the ground. First, you need to have an adaptive optics system, or you're just going to be hopeless with the atmosphere. Second, a chronograph can help boost the dynamic range and contrast. And third, you're going to be wanting to use speckle suppression techniques, such as ADI and other variants like spectral differential imaging. And I'm going to talk about basically the surveys that have occurred over the last 10 years or so, and a little bit about future surveys that combine various of these elements, and just kind of start with generation. So by generation, I mean more generation 0, let's start with that, are ones that basically just use adaptive optics, or HST. No coronagraph, no attempt at speckle suppression. So here's one example. This is a contrast curve from Masciadri et al. 2005. This was about a 30-star survey at NACO, the VLT. I guess we're a little cut off again. Oh, well. And what was that? I don't know. Yeah. Oh, well. We'll work with it. Okay. Yeah. So it kind of creeps, huh? Weird. Anyhow. So the typical contrast in this set of surveys is a factor of about 10 to the 8th. 10 to the 8th at about 0.5 arc seconds, and maybe, delta magnitude, and 12 at about 1 arc second or so. So summary on these, that was the typical contrast. The big other issue with this set of surveys is they often were very small, less than 50 stars. So here are some examples. So they were really the first set of surveys to get down to contrast where you could realistically detect planets, very high mass planets, 5 to 10 Jupiter mass or higher, at wide separations. But because they didn't look at a lot of stars and they didn't get terribly close in, these didn't really yield any detections. So that's generation 0. Generation 1 combined large telescope and AO, so that's always going to be there. But these also either used speckle suppression techniques, and one of these also did have a coronagraph as well. The sample sizes for these were higher, so they started to really start putting interesting statistical constraints on them. And the typical contrasts were more like delta magnitude of 10 or so at 0.5 arc seconds. So these included a number of the VLT, the SDI survey, the VLT, the Gemini Deep Planet survey, a number at Palomar and Keck. And this one I want to point out in particular is the first chronographic survey. It was a smaller telescope, it targeted older stars, so unfortunately didn't get as interesting depths, but this is actually the very first really truly chronographic one. And this survey here, the Heinz et al. Survey, is the first survey attempted in the mid-infrared as opposed to the near-infrared. So the two surveys of these, though, that really started opening up parameter space in terms of depth is the Gemini Deep Planet survey from Lafreniere et al. So this was 80 stars, and this was the first large ADI survey, so using azimuthal differential imaging techniques to get down to contrasts of delta magnitude of 14 in many cases further out. And closer in, there's also my own thesis survey, which was about a 50-star survey using another technique called spectral differential imaging. So spectral differential imaging, you image simultaneously inside and outside of a spectral feature you expect to see in young planets. We made a choice that in hindsight doesn't seem so great, which is we looked at methane absorption. So for methane features, we got very good contrast, but the problem is with this technique, if you don't have methane, you don't get quite as good contrast. You have to look at single bands and not do your subtraction. So that is a bit of a cautionary tale. When you are choosing a spectral feature, make sure it's in the objects you look at. So the combination of these surveys with a couple of the 0th generation surveys yielded some very strong constraints, however, on the distribution of white planets. So this is from Nielsen et al. 2010. This is a compilation of 118 stars from the GDPS survey, the SDI survey, and also Masciadri et al. 2005. And this is the result of a Monte Carlo simulation. So what you're looking at here, for each combination of semi-major axis and mass, they simulated 10 to the 5th trial planets. So taking those planets, taking the rest of the orbital parameters randomly, taking an evolutionary model to go between mass and contrast, and then using those randomly generated orbital parameters to choose random projected separation. You took that ensemble, compared it against the contrast curves for all of the different survey stars, and saw what percentage of those simulated planets could be detected or not. And given that for this 118-star surveys there was a null detection, you can then put an upper limit on the planet fraction this way. So the result of this essentially is here we have 95% confidence level here for this blue thing here. And from about 50 to about 500 AU, less than 20% of these stars can host planets at about 4 Jupiter masses. So in other words, we already knew from these null results that very wide planets, very high mass wide planets, were rare. So this is the most recent previous generation of surveys. Now I'm going to move on to talk about current and recently concluded direct imaging efforts. So again, I will remind you of the different elements of exoplanet imaging. We need the AO system, we need a chronograph, and we need to also use advanced speckle suppression techniques. And these current state-of-the-art surveys really combine all three of them. And additionally, they tend to have larger sample sizes than the previous generation of stars. They're getting typical contrasts of delta magnitude about 14.5 at 1 arcsecond. So here is the laundry list of these surveys. I'll introduce them all, but I'm going to really only discuss detailed results for one or two of them. The first is the Nikki Science Campaign. This was a 230-star survey from 2008 to 2012 using Nikki, the near-infrared chronographic imager at Gemini South. There's the NACO Large program. It's about a 100-star survey using NACO at the VLT, and it also recently concluded. IDPS is the International Deep Planet Survey. It's a large survey using Gemini NIRI and Keck. SEEDS is an ongoing but soon-to-be completed 5-year survey using Haichao at Subaru. SEEDS is likely to have the largest sample size of all of these, but while some of these other programs have really been focusing mostly on young stars and mostly on direct imaging planet detection, SEEDS has had a bit of a broader scientific goal and has yielded, for instance, a lot of really great disk imaging results. There's also a number of M-star-based surveys. Again, these other programs tend to focus on young solar analogs or high-mass stars. These are dedicated M-star surveys, maybe slightly smaller sample sizes because of this. And I also want to point out LEACH and also the Stellorbital survey are mid-infrared surveys, so working at L band instead of at JHK. The rest of these are all JHK. So I'm going to just take a moment to talk about why would you use L band instead of JHK and talk about the pros and cons of both. So unfortunately, this is kind of the most squinty of these slides. So I'll try to describe this well. In general, we get better contrast if you work in H. So these are LBT results from the LEACH survey. And you can see you just do better numerically at contrast in H versus L. And then you also just do better numerically because you have a much lower sky background at H than L. But one thing that's nice with L is that even though you don't get as high numerical sensitivity, contrast, you get similar planet sensitivity nonetheless. So here we're looking at young stars and converting our contrast into the detectable planet mass limits for young stars. And now we see L band is starting to prevail over H. And then if you look at older stars, this is where L band is particularly powerful. So because the black body peak for planets is pretty much out in L, this is really an ideal place to look for them. They're just pretty much at their brightest, even at older ages. So here, for older stars, we can see L band starts to do much better in terms of minimum detectable planet mass compared to H band. So that's one of the motivations between the people doing these L band surveys. But all of these surveys are really valuable both for detecting new planets so that we can characterize their physical properties, and in particular, really putting strong constraints on architecture of these planetary systems, whether or not you detect planets as part of your survey. So I'm going to talk about how we do this kind of statistical modeling based on results from one of these recently completed surveys. So this is the Gemini Nikki Planet Finding Campaign. As I mentioned, this was a 230-star survey that ran from 2008 to 2012. And in general, we reached contrasts of 10 to the 5, 10 to the 5.5 at 1 arcsecond, so that's about 14.5 magnitudes. And this is just a number of typical stars from the Nikki survey. Other peer surveys at other telescopes did tend to reach similar contrasts too. And at these contrasts, you really do have good mass sensitivity. So this is taking these contrasts, converting to a minimum detectable mass, in this case with a hot star model, and then looking for each survey star what the minimum detectable mass is as a function of separation from the star. So very close in, we still have pretty good sensitivity planets, higher mass planets, 5 to 10 Jupiter mass planets. And as we move further out, across all spectral types, we have sensitivity down almost to 1 Jupiter mass planets. So if they're there, we should have been able to see them with this survey. This survey, in fact, did yield a null result, but even so, it also yielded some of the strongest constraints on the distribution of young planets. So this is a subsample. These are young moving group stars, so members of young kinematic associations. So they have particularly good ages of about 10 to 150 million years. And from the null result for these 78 stars, given the contrast that we had, less than 8% can host 1 to 20 Jupiter mass planet at semi-major axes of 10 to 150 AU at a 95% confidence level. So this is a very similar result as the previous set of surveys, but a much higher confidence level. And we get even stronger results if we look at the entire survey sample. So this is the entire, about 230 stars that were observed with Nikki, as well as 50 other stars taken from the literature. So this is a similar plot as I showed before, where for each semi-major axis mass point, we simulated 10 to the 5th objects, and then you converted to contrast using models, looked at what was detectable with our contrast curves. Here are radial velocity planets, just as comparison. And again, a similar result, but now we can say at a 95% confidence level that fewer than 5% of these survey stars host gas giant planets with masses of greater than 4 Jupiter masses at 18 to 530 AU. In other words, young gas giants, very wide ones, are quite rare. But how rare they are depends a little bit in terms of what model you take to convert between mass and contrast. So again, I mentioned that some of these results are using hot start models, and cold start models give you a bit of a different parameter space. So hot start models, again, we're starting as just a big ball, puffy ball of gas and letting it collapse. So this is appropriate perhaps in the case of gravitational instability, where you have some sort of instability further out in the disk, and basically you don't have in particular a core that you're accreting on. Closer in, you might imagine a planet forms by a core accretion, accreting onto that solid core, and then starts at a lower luminosity. So we can actually use this set of models to try to distinguish between these two different formation mechanisms and the population of planets that they produce. So another thing that distinguishes between these two is that we expect them to live in somewhat different parts of their solar system. So core accretion objects should perhaps live closer in, where you have enough mass to get a solid core to accrete on. Now they can be scattered out or migrate out, but probably not that far. Whereas this instability, gravitational instability objects, should be further out in the outer reaches of the disk. And further out than that, the only way you're going to get planet out there is by planet-planet scattering. So if we look at the Nikki results using hot start models that would trace gravitational instability, what we can see is for the area of parameter space where we expect to find the gravitational instability planets, we actually have very good constraints. We expect less than 5% of these stars to have planets at, say, 100 AU with a mass of 3 or 4 Jupiter mass. Now, if we look at the cold star models appropriate for core accretion, what we see is that we aren't putting as strong constraints because we aren't yet getting to the part of parameter space where we expect to see these core accretion planets. So translating these into numbers, we can strongly say that less than 10% of stars have gas giants forming via gravitational instability, i.e. hot star planets, in quotes, from 10 to 810 AU. And we can put a similar constraint on the cold start planets, but not as strong. So less than 10% have stars have similar high mass planets from 20 to 630 AUs, but we really expect these core accretion planets to be within the inner 10 AU. So the summary of that is basically that we can say that something that's an analog of HR 8799, that system with 4 planets all very far out, those are probably very rare, whereas something like beta pic B at a separation of 8 to 10 AU may be a lot more common. And I think we actually have a really good prospect of perhaps detecting these beta pic B analogs in the next couple of years due to some of these next generation planet imaging efforts that will be coming online, or actually are pretty much online now. So here are 4 new very exciting instruments that are now all on Sky and almost all have science results on the astropage already. So SPHERE at the VLT, the Gemini Planet Imager at Gemini, Project 1640, and SKEX-AO. So again, these combine all of the different elements of exoplanet imaging, adaptive optics, a chronograph, advanced imaging techniques, but they combine two more elements. One is that these are all extremely high Strel systems, which means that the chronograph is really doing exactly what it's supposed to be doing. So I mentioned that for some of these earlier surveys, you were working at maybe 60 to 70% Strel. So your chronograph is acting a lot more as an occulter, not as a full chronograph. But in this case, the Leo stop or similar is really doing its job in all of these cases and getting very good contrast. And the other aspect that's new with these is that all of these have or are planned to have integral field spectrographs, which will allow you to get spectra simultaneously as you detect these objects. So I would like to just do a little comparison. These are first generation images of, this is the HR 4796 disk with Nikki. This is a NACO image of Beta Pic B. And this is what these systems look like in the GPI and SPHERE images. So here is the GPI image of 4796, the SPHERE image of the same disk, and the GPI image of Beta Pic. So really much better contrast. Things are just popping right out. So it's going to be really exciting. It's already really exciting, the results coming from these systems. And I'm just going to conclude by talking about the possible survey results we would expect to see out of this. So this is based on simulations of the near-SIR. I always want to say the near-SIR survey, but near-SIR actually stands for near-infrared survey. So actually saying near-SIR survey is redundant, but it is a 400-star survey predicted to start with VLT next year. And to get a sense of what planet yield we expect, we've been doing Monte Carlo simulations. So here is just results from one particular Monte Carlo simulation following the approach of Nielsen and Close and Bonavita et al. 2012. So these are just the simulated planet populations. And how do we do this? Unlike before, where we just simulated a bunch of objects at a given semi-major axis mass pair, here we make some assumption about the planet distribution. We don't necessarily have great assumptions to make, but our best prior at the moment are the radial velocity planets. So we just extend out the sort of power laws used to describe radial velocity planets out to similar separations as you'd expect for direct imaging planets. So we have a power law in mass, alpha, negative 0.63, and beta, negative 1.16, taken from the literature. So those are our first two parameters, those two power law indices. The next parameter is the planet fraction, which we basically set from radial velocity planets as well. And the last parameter is that we know that we can't just extend this out infinitely because we would have detected 1 million planets that way. So we need to cut off the power law distribution in semi-major axis. So we also have a cutoff. So we simulate an ensemble of planets in mass and semi-major axis using these different power laws. We then use evolutionary models to convert to contrast and compare against contrast curves. But we then need to also put the simulated planets around some stars. So here's one possible planet distribution. This is planet distribution from 8 to 200 million years old. I mean, population of stars. It really has crept up again, hasn't it? How much time do I have? Is it worth it? About 11 minutes. Okay, let's try it again. So this is just one possible survey sample of stars with ranges from 8 to 200 million years, generally within 200 years. They're generally young moving group objects. That didn't work this time. No worries. It's legible enough. And they're also a range of different masses. This is just one possible survey sample, and if we put our simulated planets around these survey stars, then compare with a predicted contrast, we can then make a prediction for the number of planets we should detect. Some of these are more realistic models than others. So these are, again, the same set of power laws with semi-major axis cutoffs of 20 to 50 AU. We already have ruled this one out from the previous generation of models. And if it was true, we'd be expected to detect between 40 and 70 planets. But for more realistic cutoffs, say 20 AU, we do expect to have about 10 to 30 planets. So these are not making any scaling versus the primary mass. And this is the second set of models where we've scaled the number of planets so that higher mass stars actually preferentially host higher mass planets. So given this range, we would expect to detect between 10 and 30 planets in this survey. So these upcoming surveys will literally double the number of young planets that we know about. And actually, I think I'm about to end right there anyhow. So conclusions here is that as we detect more and more of these planets, we learn more about their physical properties, which Travis is going to tell us about very soon. And that's one real reason to conduct future surveys, as well as to really start getting more than just the outliers. We know things like HR 8799 is rare. We'd like to move closer in at higher contrast and figure out what is more typical. And the real benefit of doing surveys is that we can really start constraining the architecture of these systems. We already know that hot start gas giants are quite rare at wide separations. And it'll be really exciting to see what we can say about planets at more moderate separations and higher contrast as well. Thanks, everyone. Okay, so the question was how much of the SPHERE near-infrared survey will overlap with the Nikki campaign and with the future Gemini GPIs survey. Likely a lot, especially between the SPHERE and the GPI surveys, just because we will be sampling similar parameter space. With Nikki, less so. One thing with these newer imagers is that they don't actually have particularly large fields of view. So the IFS in particular are limited to really the inner arcsecond, whereas Nikki had a much larger field of view of 10, 20 arcseconds. So it was putting much more constraints on wide planets, and the next generation really will start constraining much closer in. Okay, so first question was, are there surveys targeting other parts of parameter space, for instance, tidally heated moons? Second question was, how do you distinguish observationally cold start versus hot start? So starting with the first one, I believe Ed Turner and collaborators are trying to start exactly this kind of moon survey. I think it's called THEM, tidally heated exomoons, but I think that's still in its early stage. There are other surveys that are definitely targeting different parts of parameter space. For instance, Justin, I know you've been working a lot with RV trend stars. So these are older stars, but they have evidence for a trend in RV that hasn't had a full period, so evidence for a further out companion, and there's a number of groups that are searching for those companions with AO and using similar techniques. So the second question, telling the difference between hot start and cold start, this is tricky because we really don't actually know for any given planet. We just see what we see. We can do something like what I did in this talk, which is say, okay, we expect gravitational instability to be hot start, we expect core accretion to be cold start, but often we get surprises. So, for instance, the HR 8799 planets, they seem to be well defined by hot start models, but for their effective temperature, we would have expected them to be T-dwarfs. So there's still some inconsistencies there. Okay, are there any good systems that really give you a constraint as to whether they're hot start or cold start? I think of the current set of directly imaged exoplanets, some look more hot starty, some look more cold starty. So it's all very early days. I'm sure Travis will have more to say about this. But for instance, the HR 8799 planets look very much like they would form by hot start. They don't have methane absorption. They're redder, they're fairly bright. The only planet out there that really looks cold start-like would probably be GJ504b. It's the only one that has methane absorption, or a claim of methane absorption detection. But again, it's early days. The planets we've detected are the outliers. And as we do more of these surveys and move closer in, we'll have a better idea because we'll have more idea of what is a typical directly imaged planet.